Welcome to CHEM is Try. Today, we are talking about the standard hydrogen electrode and its significance. In our previous video, we had a chat about some elements, their reduction half equations, their standard reduction potential values, and their standard oxidation potential values. But it was for only one element each. For instance, we had lithium. So how could we have determined the standard electrode potential value for lithium? We should have hooked it up with something else. But what else can we hook up the lithium cell to? That will help us to know the ability of lithium to lose electrons. This is it, the standard hydrogen electrode. It is called the reference electrode. It is also abbreviated as SHE. So from now, I'll be talking about SHE whenever I want to talk about standard hydrogen electrode. This is how the standard hydrogen electrode looks like. It is made up of a piece of platinum wire connected to a metal which has been coated with platinum black. We have a glass tube that is used to cover the coated metal and the wires, and they are placed in 1 molar H+ solution. 1 molar H+ solution is the same as 1 mole per decimeter cube hydrochloric acid solution, or 0.5 mole per decimeter cube sulfuric acid solution. This occurs at a temperature of 298 Kelvin and a pressure of 1 atm. Hydrogen gas is thus bubbled through this glass. That hydrogen gas will move to where we have the metal coated with platinum black S. The solution is made up of H+ ions, and we have hydrogen gas bubble through. When this reference electrode is hooked up to another electrode, two possible reactions could occur. It's either an oxidation or a reduction reaction that will occur in the standard hydrogen electrode. In the case of oxidation, the hydrogen gas over here would lose 2 electrons and become hydrogen ions. So the hydrogen gas over here will reduce, and the hydrogen ion concentration in the solution would increase. But what would make oxidation occur over here? We'll look at that one very soon. If it is hooked up to another cell, another thing that can happen is the reduction of hydrogen ions to hydrogen gas. The hydrogen ions will then gain 2 electrons and form hydrogen gas. So when that happens, you are going to see hydrogen, bubbles of hydrogen gas all around the piece of metal coated with platinum black. So always look out for this. If you hook this one up with a different cell to form a galvanic cell, one of them will have to lose electrons, one of them will have to gain the lost electrons. How would you know which process is happening over here? One thing you have to look out for. If it is reduction that is happening over here, you will see bubbles of hydrogen gas formed all around the platinum black surface. That is what will show us that reduction is truly occurring in the SHE. However, if oxidation is occurring in the SHE, you will see no bubbles of hydrogen gas. So the moment you hook it up with another different cell and you realize there's no bubbles of hydrogen gas, remember, it is undergoing oxidation. That means the hydrogen gas is now losing electrons. Can we use the SHE to measure the standard electrode potential value of other electrodes? One thing we need to become aware is that it has been internationally agreed that the standard electrode potential value of this She is 0.00 volts. So whether oxidation of hydrogen to hydrogen ions or reduction of hydrogen ions to hydrogen gas, the standard electrode potential value over here will have to be 0.00 volts. So with knowledge of this one, we can hook it up with another cell, then find the total EMF and use the total EMF to find the electrode potential value of the other substance. The formula is simple. The EMF of the cell will be the sum of the standard reduction potential value and the standard oxidation potential value. But we said something. We said the electric potential values we are given will always be given to us as standard reduction potential, not standard oxidation potential. So, standard oxidation potential we know to be the negative of it to give us the standard reduction potential. We know that. Therefore, we can say that the EMF of the whole setup can be given as the standard reduction potential of the reduction reaction. And the reduction reaction we know is called the cathodic reaction. So the standard electrode potential at the cathode minus the standard reduction potential value of the anode. Minus because it is supposed the standard of oxidation potential, but we are expressing it always as standard reduction potential. So minus standard oxidation potential value will give us standard reduction potential value. It is negative because the standard oxidation potential value can be related to the standard reduction potential value. And this is the relationship. Negative standard oxidation potential value is equal to standard reduction potential value. So this is the anode. This is the anode. This is the cathode. But we are saying that the value over here will not be given as standard oxidation potential. No, it will be given as standard reduction potential value. So this one becomes negative for it to become standard reduction potential. And that is the anode. So the EMF of the whole cell setup will be equal to the electrode potential at the cathode minus the electrode potential at the anode. Let's keep this formula in mind. This is how we will be able to identify the standard reduction potential value of a cell connected to the She. A classical example of She in action is the zinc She cell. Let's assume we have no idea what the standard reduction potential of zinc is, and we want to determine it. This is how we do it. We take a beaker, then we fill it with zinc sulfate solution, 1 mole per decimeter cube zinc sulfate solution. Then we place our zinc metal as electrode inside the solution. We hook it up with the She electrode. And we place a voltmeter here to measure the electrode potential in volts for us. When we put in the salt bridge and connect the wires, there are some things that will start occurring. You realize that the initial electrode potential that will be read by the voltmeter will be positive 0.76 volts. That is the electrode potential for the whole connection, the whole cell. Then, this zinc in time will will become smaller and smaller and smaller. It begins to shrink. It shrinks, telling us that some of the zinc atoms in the zinc metal are losing electrons. So you have zinc losing 2 electrons to form zinc 2+. Let's write it well. Zinc going to produce zinc 2+ plus 2 electrons. Solid, and this is aqueous because the electrons, when electrons are lost, the zinc 2+ form enters the solution. So what we will be observing is that the zinc metal will begin to shrink in size. Then at this side, we will observe more bubbles of hydrogen gas produced around the metal coated with platinum black. And what did we say about bubbles being formed? When bubbles are formed around the platinum black, what it means is the hydrogen ions in the solution are now gaining electrons to form hydrogen gas. So the zinc will shrink in size. That means the concentration of Zn2+ will increase over here in this solution. Over here, we'll be seeing bubbles of hydrogen gas. That means the concentration of H+ ions over here will reduce because the H+ ions are being converted to hydrogen gas. When these things happen, it tells us that over here, zinc's oxidation number is increasing from 0 to +2. So this one is the site of oxidation. When hydrogen ions gain electrons to form hydrogen gas, the oxidation number of hydrogen reduces from +1 to 0. So reduction is occurring here. That would mean that this one will be the anode and ox, and this one will be red cat, our cathode. Can you see it? So this is what we identify this as the anode and this as the cathode, meaning electrons are being lost from the zinc and given to the hydrogen ions in solution to form hydrogen gas. These are the half reactions. When we combine the half reactions together, we get the overall reaction. Zinc plus 2H plus 2 electrons going to Zn2 plus 2 electrons plus hydrogen gas. Electrons are common in both sides, we cancel them out. This becomes the overall reaction that is occurring in the zinc She cell. But how are we going to use this to determine the electrode potential value of zinc? The EMF of the whole cell, we said, is giving us the electrode potential at the cathode minus the electrode potential at the anode. And from this connection, this galvanic cell, we can say that the anode refers to the zinc compartment and the cathode refers to the She compartment. The total EMF of the whole voltaic cell is positive 0.76 volts. The electrode potential of the cathode, our cathode is the She, and it has been internationally agreed that the She as a reference electrode would have a standard reduction potential of 0.00 volts. So it is left with the standard electrode potential of the anode, which is the zinc half cell. Therefore, the standard electrode potential value of the zinc half shell becomes negative 0.76 volts. You can check the previous video and look at the chart. You will realize that the standard reduction potential value of the zinc electrode is negative 0.76 volts. Now, that is how they came by that value. In this case, the sheet served as the cathode, and the electrode, whose electrode potential you wanted to look for, served as the anode. What if the sheet becomes the anode? Let's look at another example, the copper sheet cell. We want to determine the electrode potential, the standard electrode potential of copper. So we take a beaker, we fill it with 1 molar copper sulfate solution under a temperature of 298 Kelvin. Then we place our copper electrode inside. We hook it up to the sheet. Then we connect our salt bridge. After connecting these two cells together, there are some things we observe. One, the initial electrode potential is read as positive 0.34 volts, and that represents the electrode potential for the whole setup. Then we wait for a while. We see no hydrogen bubbles over here. But you realize that the copper metal gets bigger and bigger and bigger. What does it mean? The copper is getting bigger because the copper ions in the solution are gaining 2 electrons to form copper metal. The oxidation number of copper is increasing from +2, so it's decreasing from +2 to 0. That means reduction is occurring here in the copper half cell. And what did we say about reduction? The reduction cell is called the cathode, red cat. The bubbles of hydrogen gas that were passed through the glass tube lose electrons to form hydrogen ions. We can appropriately write this equation as the oxidation number of hydrogen is increasing from 0 to +1. So this is an oxidation half cell. And the oxidation half cell we call anode. So what it means is the hydrogen gas that will bubble through this platinum, through this glass to the platinum black, begins to lose electrons to form hydrogen ions. So the concentration of the hydrogen ions in solution over here will begin to increase, but we wouldn't see that, would we? Hydrogen gas is being converted to hydrogen ions. But this one, we are going to see it because the copper will start to become bigger and bigger and bigger than it was before. The overall setup will have an equation of hydrogen gas plus copper 2 ions in solution plus 2 electrons, producing 2 moles of hydrogen ions in solution, plus 2 electrons plus copper metal. We have 2 electrons on both sides. They can cancel out. And our overall reaction becomes hydrogen gas plus copper 2 ions in solution, going to produce 2 moles of hydrogen ions in solution plus copper metal. What did we say about the EMF? We said the EMF of the whole cell is giving us the standard electrode potential of the cathodic half cell minus that of the anodic half cell. And from our hookup, from our connection, we realize that the anode is the sheath and the cathode is the copper compartment. So, our total EMF was originally recorded as positive 0.34 volts, and it's giving us the standard electrode potential of the cathode, which we are looking for, minus that of the anode, which is the sheath. And remember, it has been internationally agreed that the sheath as a reference electrode has electrode potential value of 0.00 volts. We can then find the standard electrode potential of our cathode, which is our copper compartment. So the standard electrode potential of our cathode becomes positive 0.34 volts. You can check the previous video and look at the chart. You would realize that copper has a standard reduction potential value of plus 0.34 volts. And this is how they came about the standard reduction potential values of all those elements that were presented in the table. In our next video, we will be considering the uses of the standard electrode potential values. We are also going to consider calculations involving standard electrode potential. Thank you.